activity since this is Friday. Let me say that I got it. Since this is Friday, almost evening, right? So is this gonna work? Let me stop this share and then go here and just show this. So this is what mathematics is for me, and I am really happy when I meet people that are like-minded. All right, let us go back to the talk. No, so I took it from a friend, so I don't put the credits, but then a friend of mine drew it for me. Thank you. Review. All right, so I'll talk about extremal cuts. All right. So I'm going to talk about combinatorial optimization in this talk. And so I'll be considering a graph that is k-regular on n vertices. And these are the quantities. So this is the first quantity I'm going to be trying to look at is maximum cuts. Many of you know this. By the way, I apologize, like maybe 2 or 3 of you have already seen this talk in this audience. So for the rest of the people, perhaps this is going to be somewhat new. So for maximum cut, I'm looking to partition my vertex set into 2 sides, such that the number of vertices that cross the partition is maximal. Okay, so you can encode this as a spin system where I'm going to assign a plus to one side of the partition and a minus to the other side. And I can write a formula. This is a formula for the maximum cut of a given graph G. So it involves the Laplacian of the graph. So we've seen this morning. And here I'm going to be optimizing over binary solutions. Right? The next quantity that we're going to look at in this talk is minimum bisection. So I'm still going to try to partition my vertex set into 2 sides. Here I want the crossing number of edges to be minimal, but I'm going to have to impose an additional constraint. Otherwise, the problem is trivial. And the additional constraint will be that the cut has to be balanced. I need the same number of vertices on one side or the other. Here, okay, so this imposes a constraint on the number of vertices for them to be, even. But if it's not even, I can just, put this on the other side and ask that the sizes differ by most one, which is okay, which is fine. So the minimum bisection can be written also as this explicit combinatorial optimization problem, minimize the Laplacian such that the sum of the spins is 0. So of course, these problems are intractable in general. This one is NP hard or short P hard, NP hard, to decide whether a solution, to find an actual solution. But here I'm going to restrict my attention to a special class of graphs, which have been mentioned many times in this meeting, so locally-treelike regular graphs, and we can see what we can do on those graphs. So what is the definition of a locally-treelike graph? We're going to say that a graph is L, epsilon locally-treelike if around n 1 minus epsilon fraction of the vertices I, the ball of radius L around them is isomorphic to a tree. You can think of epsilon to be 0 if you'd like, in which case, this means just that the girth of the graph is larger than perhaps 2 times L or something like that. And of course, prototypical example of a locally-treelike graph is the random regular graph, or any model of the random regular graphs, perhaps those that we've seen this morning. For any epsilon and any L, the random regular graph has this property for some n larger than, large enough. And the question that we'll be asking is, can we efficiently compute these combinatorial quantities on this class of graphs? So the first question that perhaps we should ask is, what is the value that these 2 optima achieve? Are there any explicit quantities that we can shoot for? Because if you have a value, then you can try to compare whatever your algorithm outputs, you can compare it to that value and say whether you're optimal or close to optimal, half optimal, etc. So the asymptotic values. So we're going to look at random regular graphs, and we're going to look at the asymptotic values of these quantities. So let me put expectations in front of these quantities. They concentrate, so this is not a big deal. Turns out that the max cut value is known to converge to some constant C+, and the existence of this limit is due to some beautiful work by Ati, Gamarnik, and Teveli. And this uses a very nice interpolation argument that splits the graph into two halves and then argues that this quantity is perhaps sub-additive or super-additive. I don't remember, one of them, and super-additive. Curiously enough, the minimum bisection is not known to have a limit. And this is because of this breakdown of the argument of the interpolation. And this is perhaps if you've seen Will's talk, he had a lot of conditions on the convergence of the free energy of his model. And one of those conditions is supposed to rule out this type of example. So this is a bad example for Will's theorem to hold. And we don't have this, just means that we don't have enough tools so far to deal with this type of models. Many models we would like to say that they converge, but just the existence of the limit is not known. So this is a lack of theory in spin glasses. There's a beautiful conjecture that relates these two quantities for the regular model, when k is fixed, is that when you sum these two quantities, you get half the number of edges, or the number of edges, k over 2. So I'm dividing by n. You should think of n times this times n times this equals nk over 2, and that's the number of edges. So this is a beautiful conjecture from physics that is based on the cavity method, and this should hold for every k that is larger than 3. And there is some efforts from many people to try to prove this. So far, this is a conjecture. But one question that you can try to ask to make this easier is to say, okay, can I prove this for k large? Can I get any hold on this conjecture for a large degree k? There's a partial solution that is given by a nice theorem by Dembo, Montanari, and Sen that tries to compute the asymptotic expansion of these two quantities in k. Okay. So this is what they get. They get k over 4. K over 4 is half the number of edges, which means that this quantity is trivial. It just means that if you partition the graph at random, you'll get on average half of the number of edges that cross your partition, your random partition. The next term is non-trivial. The next term behaves like square root k. So you go from k to square root k, and there is an explicit constant up front, p star. And then the next order term is some little o of k, right? Square root k, excuse me. And similarly, from min-bisection, there is a minus, so that if you sum them, you get k over 2 plus a little o of square root k. So they partially prove the conjecture in this k, large k limit. We don't know, by the way, what this term should look like. There are some conjectures, but yeah, we don't know rigorously what this should look like. I want to point your attention to this particular number. It's called the Parisi constant, and I'm going to explain where it comes from. Its numerical evaluation is 0.7631. Okay. Please stop me at any time. Yeah, I'm happy to not go through the entirety of the deck. This is Friday at 5. So where does the P star come from? It comes from this model that is called the Sherrington-Kirkpatrick model. So let me introduce it. So it's almost the same optimization problem, except that instead of looking at a random graph, the adjacency matrix of a random graph, I'm looking at a GUE matrix. So look at a GUE matrix and try to maximize this quadratic form over the hypercube. Divide by n for scaling. And then there is a famous theorem. So this has been, the value of this has been predicted by Parisi, from the 70s, and there's been a lot of work in physics to understand the fine structure of the set of solutions. So Legrand and Guerra proved that this optimum converges in whatever sense you'd like to this constant P star. There is a bigger optimization problem that is behind that I'm going to explain a bit better later. Okay, so why does the P star show up in these formulas? So let me just give you a heuristic. So based on this result, let me give you a heuristic. It's basically when k is large, you can replace the adjacency matrix by a GUE. That's it, right? So if you look at a graph and at an assignment sigma, I can write the cut. This is the Laplacian. I'm just putting the 101 minus sigma j over 2. I'm just putting that 1 to the outside so that I have a quadratic form in the adjacency matrix, right? I'm not going to look at that term. So this is the quadratic form in the adjacency matrix. This is my adjacency matrix. And now I'm going to normalize it, the adjacency matrix. I'm going to standardize it. I'm going to write it in this form where A bar is just this standardization, right? So if I just expand everything, I get this A bar here. And then by the central limit theorem, if you believe the central limit theorem, when K is large, I can replace this A bar by a GOE matrix. Now I get this term for min bisection, I constrain this to be 0, so it goes away. But for max cut, you should expect, or we should expect, that the optimal partition in a maximum in a random regular graph should be balanced, which means that this sum should be of order little o of n. So when we square it and then you have n squared, this goes away. Okay, so that's why you get the optimum of the SK model in front of square root k minus 1 over 2 here. And now that we know that this converges, then this is the value that you shoot for. So that tells you why there's a p star in the asymptotic expansion. Does that make sense? A bar. A bar. No. This is a physics argument. I'm not saying this is the proof. No, this is not the proof. Yeah. This is they prove it in a different way by interpolation. There's a lot of machinery that goes into this proof. Yeah. I'm just saying this is what you should expect based on this. So there's a Lindeberg part of the argument that perhaps that what the CLT here means. And there's this part where you interpolate between the dense and the sparse model. So we interpolate between SK and the diluted, whatever, antiferromagnetic Ising model or something. There's an interpolation between them. And then you have to do some kind of Lindeberg arguments. There are two arguments there. So yeah, I think that oh, okay. So maybe I'm not aware of that one. I'm not aware of that one. I should read it. Yeah. All right. Thank you. That would be nice too. Yeah, I'm not aware of that one. Thanks. Other questions? So the main result that I would like to discuss today is that this proof can be made algorithmic, which means that there exists a local efficient algorithm that on any L, 0, let's say just L local algorithm or L locally-treelike graph G. Here, L, 0 means that the girth is at least 2L. You can put an epsilon here if you'd like. It doesn't matter too much. That epsilon will show up in the error. So let's just, for simplicity for this talk, let's just look at graphs that have high girth. They're k-regular. There exists an algorithm that outputs some partition of the set of vertices such that the cut is almost what you should expect from the theory, right? So if the locality of the algorithm, the ball that the algorithm is allowed to look at to decide the spin of the roots grows like L, then that as L increases, then that you approach the right constant. Okay, and the errors are in K and in N. So you should think of N goes to infinity first, then K goes to infinity second, then L goes to infinity third. So it's a triple asymptotic regime. Okay, and this result is, well, our theorem is not true. We cannot prove it for fixed K. So it really crucially relies on letting the degree grow to infinity. So this is the same, perhaps the difficulty is at the same level of perhaps Jungtag's talk, where the proofs only work when the K in K-sat is large. So it's the same type of difficulty. So what is this asterisk here? This is under an assumption. So this theorem is conditional. It's under this assumption that is called the no overlap gap property for the Parisi formula. So I'm going to try to explain what those things are. No overlap gap we've seen this morning. But it takes another form in this full RSB model, and I'll explain what that means also. And let's get into it. Perhaps before doing that, so some consequences under this assumption of no GP. This algorithm is, as we've seen, it's nearly optimal on random regular graphs. So the algorithm applies to all graphs that are of large girth. But in the particular case of random regular graphs, it's optimal because that's the value, okay, up to those errors, little o of n, little o of square root k, etc. And this algorithm is also the best among local algorithms for locally tree-like graphs, because as far as a local algorithm is concerned, when you give it a locally tree-like graph, it might as well assume that it's a random regular graph, right? Because it only sees a bounded region, and that bounded region is isomorphic to a tree. So as far as the algorithm is concerned, any locally tree-like graph looks like the tree, right? So this is the best value that a local algorithm can achieve. So as a consequence of that, maximum cuts, the functional maximum cuts as a function of graphs, is minimized by random regular graphs, right? And in the opposite direction, minimum bisection, the functional minimum bisection as a function of graphs, is maximized for random regular graphs. So the extremal graphs for these combinatorial quantities are random regular graphs, right? So this is acting to the Ramanujan property for the second eigenvalue. So we learned this morning that the Alon-Bopana bound tells us that the second eigenvalue of a random, or not random, but any sequence of graphs of diverging size has to be at least 2 square root d minus 1, right? And random regular graphs almost achieves that bound. So this is a combinatorial version of that result that doesn't concern the second eigenvalue. It concerned another optimization problem or another characteristic of a graph, which is maximum cut, if you would like minimum bisection as well, right? Make sense? Yeah. Yes, yes. Yeah, locality. You have to look at larger and larger neighborhoods to decide the spin of the roots. Three limits. Yeah. Yeah. N large, K large, and then L large. No, 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 no. I don't have to do that. So that's perhaps, I'll rephrase your question as an open problem at the end, perhaps. Yeah. Yeah. So what is the Parisi formula? Parisi formula is this optimization problem over functions. And this P star is defined as the infimum of a certain functional P of gamma of over the space of functions. So what is the space of functions? The space of functions is, okay, functions from 0, 1 to R plus, which are increasing or non-decreasing, they're L1. And this P of gamma, perhaps you don't have to read this, but it's some functional that involves some kind of nonlinear PDE, some nonlinear PDE. So for any fixed gamma, you have to solve this PDE and you get the solution phi. So gamma shows up here in the data. The data gamma shows up in the nonlinearity, in the grad squared. You solve this from this terminal condition that gives you a phi, function phi of 2 variables, t and x. That's a function of gamma. So if you change gamma, phi will change. And evaluate it as 0, 0, and then subtract this linear term in gamma. So this is the Parisi functional. And this P star is the infimum of this functional over this space. Okay. Okay. So what do we know about P, the functional P? There's a theorem that says that this functional is strictly convex, which is very nice, right? So if you want to minimize a convex function, that's you're in good hands. This implies in addition to some other arguments about U is an open set, so that's that may be a problem. There is a unique minimizer, so you're going to have to approximate U by a sequence of closed sets and whatnot. And so we're going to say that there is no overlap gap. The condition of having or not an overlap gap in this model refers to the structure of gamma star. So if gamma star is a strictly increasing function, we're going to say that there is no overlap gap. Okay, so that's a definition. And so what should we expect? So here we have no OGP if gamma looks like this. So one thing that you can show is that gamma has to be close to zero at zero. It has to blow up at one. So these are things that are easy to show. And we're optimizing over the space of non-decreasing functions. So which either looks like this, or maybe with other steps, multiple steps, right? This is the picture that is expected. And a picture where this is false is where we have a plateau or multiple plateaus, if you'd like. So we're going to say that there's OGP here and no OGP here. This is what's expected, and this is a major open problem in this area to show that the solution to this variational problem actually looks like this. So this is not known. And of course, what we've seen this morning, the presence of OGP, although it wasn't defined this way, or some variant of OGP, implies failure of stable algorithms. So this is perhaps the other side of the coin that says that if you don't have OGP, there is an algorithm, right? So this is the other implication. So why do I call this OGP? What does it have to do with the pictures that David drew this morning? This is, you should expect this, or a rescaled version of this function to be a CDF, right? So if I scale by beta, so here you should think of, let me try to do this here. If I'm at positive temperature, not zero temperature, this gamma actually is a CDF. I'm optimized over the space of CDFs. So from 0, 1 to 0, 1. And CDFs are increasing or non-decreasing functions. They're 0 at 0 and 1 at 1. And when I take the temperature to 0, this is the scaling limit of a sequence of CDFs. And it looks like this. It blows up. So this is a CDF of what? This thing like this or like this. If you take 2 points from the Gibbs measure, that is a temperature beta, and you look at their overlap, so their inner product, divided by n, the law of this is a random variable that happens to not concentrate. Okay, so this random variable never concentrates. And when you look at if it's annealed CDF, when I look at, so this has some CDF Fn that converges presumably to some CDF F infinity. If I look at the expectation of F infinity, this is what that is. Okay, so if the curve is strictly increasing, that means that all overlap values are allowed, right? If the curve has a plateau, that means that this interval of overlaps is not allowed, right? The CDF does not charge any points in this interval. So that's the same thing that David told us this morning, right? So this is the connection. Okay, is this clear, more or less? No? Yes? Right, so you guys know what local algorithms are, but okay, so logarithm is a local if it has the following structure. So I'm on a finite graph, so let me define this on a finite graph. I'm gonna draw IID labels for each vertex. Omega I is in some probability space. Let's just say they're Gaussian, real Gaussian. And my algorithm is gonna correspond to taking a function FL and applying it for every vertex I. And I apply this function to the random variables that are inside a ball of radius L of that vertex, right? This function takes in the neighborhood and the labels of the neighborhood and outputs a value, right? This function has to be deterministic, and it has to be the same for every neighborhood. So I'm not allowed to pick a different function for different vertices, right? So this has to do with automorphism invariant. The law has to be automorphism invariant, right? When you take the limits. So this is what a local algorithm is. And I claim that the theorem that I showed you is realizable by an algorithm that looks like this. So this is the class of iterations that we're going to look at. So this is perhaps reminiscent of Kafita's talk a few days ago. So what are message passing algorithms? So we're going to look at a graph, and we're going to put directed edges. We're going to just direct the edges in both directions. So this directed graph has twice the number of edges than the original one. And we're going to make nodes exchange messages. So at time t+1, you look at the neighbors. So if so I have a picture. So I will send a message to J by collecting the messages from its other neighbors, except J, at time t-1, does some function here, and then sends them. Okay, so every vertex will do this. Okay, let me go back to the definitions. And so I will collect the messages that come from its other neighbors than j, puts them here, multiplies by some function that is history dependent, that depends on the entire history. So the problem is not Markovian. You have to depend on the entire history to do anything non-trivial. And then you send the message and some normalization. And when you look, you can, instead of removing a vertex here, you can just sum over all the neighbors, and that gives you a value, a statistic for a particular node. So you can do this iteration and then do this one as well. So that gives you an algorithm. So I'm going to have to do something with these UIs, and you can initialize with IID. So this is the omega i's that I showed you. So these are the omega i's. And then I'm going to have to do something with these. So I'm going to combine them in a certain way. I'm going to form some kind of martingale that is history dependent. And then I'll run this algorithm for t steps, and I'm going to take delta small. I'm going to explain some of these. Some of these I'm going to explain, some of other things I'm not going to explain. But this is the general class of algorithms that I'm going to consider. And the degrees of freedom that you have is choosing these functions, this one and the previous one. So we're going to have to choose them in a clever way. And this f, this is the degrees of freedom that you have, choosing this function and the other function. So this is a general class of algorithms that can be used for almost anything on a graph. And we're going to try to use it to compute the optimal cut values. So before this, let me show you a preliminary result that was proved by Russ Lyons. And instead of the p star in the formula, he gets 2 over pi. So the formula that the algorithm that he gets, or that he devises, gets 2 over pi instead of p star. And so he described this as a factor of IID. You can also describe it in a finite graph by taking these particular choices. So my a's, let me go back. Here, it's just simple. This a is just 1. You just look at the messages and sum them. You don't multiply by anything. This function is trivial here as well. And then this function h will be chosen in a very simple way. It's a linear function. All right. So sorry. So the b's are actually just constant. They depend on t, and delta doesn't matter. In which case, what you're doing is really you're just looking at your neighbors, summing all the labels of your t neighbors at a certain distance, and then multiplying them by some numbers and summing them. So perhaps I should draw a picture to explain this. So you're trying to decide what the spin of the root is, and you have vertices around you at equal distances. So these are concentric circles at a certain distance. This is distance 1, distance 2, etc. You're looking at the labels of the vertices at this distance, you're summing them. That gives you one number, UL1. And you're looking at the labels here, and you're summing them. That gives you, etc. So that gives you a statistic, distance L, distance L prime, etc. And I'm going to just multiply these by beta 1, beta 2, beta 3, and then summing them. Okay, so this is what Z is. Okay, so I'm going to have to choose these betas. But let me, before discussing what the choice is, let me try to compute. So this is a Gaussian process. Do you agree? This is just a Gaussian process. And now if I compute the correlation of this Gaussian process over an edge, so if I look at the IZJ for an edge IJ, this is just linear algebra that gives me a certain operator that involves beta. So if I try to look at the beta that is an eigenvector of this operator T, that would give me a value, right? So the T that I get from this simple computation is this one. So it's just a simple operator that has ones above and below the diagonal, zeros everywhere else. If I choose this to be an eigenfunction with eigenvalue rho, it happens that this has eigenvalues between -2 and 2. That gives me an average correlation that is rho square root k minus 1 over k. So if this was 2, it would be the spectral radius of the tree right here. So this thing has a name. It's called the Gaussian wave function that was devised by these people on the infinite tree. So what I showed you is just an approximation on a finite graph. And the eigenvalue of this process, so for every row, there is such a process for an eigenvalue that is this row times square root k minus 1. So what does Russ lines prove? It proves that if you take rho to be -2 plus some little o, you get a Gaussian process that is related to this eigenvalue. Then you can just truncate it. You can just look at the signs. Okay, and based on the signs, you can decide which side you are on in the partition. And if you compute the value of that cut, that gives you the 2 over pi because of arc signs and whatnot. You get 2 over pi. Okay, so 2 over pi is 0.63, and you compare it to the optimal value, which is 7.6. So it's pretty close. So now you can imagine that if you want to achieve this value, somehow this value is related in an implicit way to a PDE. So somehow in your choice of these functions, the PDE has to show up, right? So you're going to have to make this PDE show up in the algorithm somehow. Okay, so how do we improve over this? So instead of taking neighbors and summing these Gaussians and then multiplying them by numbers, we're going to have to do something a bit more complicated. So now to construct a certain martingales or sequence of martingales over this graph. So every vertex will be, we're going to just diffuse a certain martingale, construct a certain martingale on that particular vertex. And we're going to make them, so these martingales have to be coupled, and they have to be coupled non-trivially. So what do I want from these martingales? So I want them to, as I let t grow, I want to converge to a ±1. So that will be the spin that I would like to have, either +1 or -1. And what do I want furthermore? I want the correlation over an edge to be maximal. So if I'm looking at max cuts, I would like the correlation to be minimal. So that's why I'm putting absolute value. If you want looking at minimum bisection, you would like this to be positive and large, right? So perhaps you can just think of at maximum cuts where you're looking for this quantity to be perhaps negative and very large in the negative direction. Okay. Does that make sense? So this is what you want. This is an optimization problem. If you can find a martingale that satisfies these two properties, you get an algorithm. So one question that you can ask is, what is the maximal edge correlation for a factor of IID? Right, so I want to optimize this quantity over factors of IID because I'm looking at local algorithms. So this is the first question you can try to ask. And there is a simple lemma that answers this. If you let Z be a factor of IID on the infinite K regular tree, if it's centered, variance 1, then on an edge, the correlation on an edge cannot be more than 1 over K times the radius. Okay, so this is not very difficult to prove. You can prove it using by approximating the tree by a random regular graph of very large girth, and using Friedman's theorem actually to prove. So this is where this thing comes from. So this is the most it could be correlated. It cannot be correlated more than that. So if you look at Lions' construction, it does achieve this bound because it turns out that this is the eigenfunction that achieves this bound. It does achieve the 2 square root k minus 1. But the problem is that these are not ±1 things that you construct with Lions' approach. They're not ±1. So if you want to make them ±1, you have to take their signs. But then if you take the sign and then do the same thing, so sigma I, sigma j, then that destroys this optimality, right? So you get the 2 over pi. Right, so when you take the sign and you do the same thing, you get a factor of 2 over pi times the optimal thing. All right, so I state again the problem, right? Over the space of factors of IID, can you maximize this correlation over an edge such that I am forcing you to have ±1? So the IID, the process has to be binary valued almost surely. So this is the problem that we're trying to solve here. It's an optimization problem. I don't know the solution to this problem for every k. I only know the solution for large k. Right, so this is where the P star will come from. So we're going to import the solution from the SK model for k large. Okay, so let me tell you about this full RSB stuff. So we've seen these cartoons in a few talks about these bubbles, and then they shatter, then they condense, and then they evaporate. And one that was interesting that Will and Young-Tak talked about is the condensation regime, where you only have finitely many clusters that take up 99% of the mass of the solution space. So this was one RSP. And when you look inside any of these, so there is, if you draw a point at random, you have a positive probability to fall in any one of these. And when you look inside, you restrict yourself to what's inside, then the model looks replica symmetric. You have your observables concentrate. If you draw 2 points from this cluster, then their overlap will concentrate, right? Their distance will concentrate. So this is one RSB, but here we're looking at a model that is a bit more complicated, which is full RSB. So at a first stage, it looks like this, but then when you zoom in a cluster, you see the same picture. And then you zoom in on that subcluster and you see the same picture infinitely many times. So if a model has that property, we're going to say that it's full RSP. So what I'm saying here is that SK is of that type, and maximum cuts on a sparse random graph is expected to be of that type. But we're very far from any type of proof of this statement. You're going to see condensation at every so you can arrange these clusters in a tree. So that's the tree that I'm drawing here, and then you'll never see a pure state until you go to infinity. You're right? Yeah, yeah. Yeah. That's what you see. Yeah, that's what you see. That's what you see. And the law, so we can look at even the law of these, the joint law of the sizes of these clusters in the tree, indexed by the tree, that is given by what's called the real probability cascade and all of that stuff. And so we understand this picture very well for in the dense case, and that's why the solution, that's why we're able to solve this problem in the dense case. But trying to understand this for the sparse case is wide open. There is nobody has no idea how to approach this in the sparse case. So you have this tree that branches infinitely often and that breaks apart infinitely often. And at the very bottom of the tree, we should think of this one. So I'm just rescaling time here. You should think of this going to infinity. At the bottom, the very bottom of this tree, you have binary values, plus minus 1. And at any level, constant level t of this tree, so these are the barycenters of these clusters that I'm going to call MT, and you can associate them physically to points inside the cube, inside the unit cube. Okay. So you're starting from the origin, and then every MT is a point inside the cube, which is supposed to be the barycenter, like the geometric barycenter of all the points that are inside this cluster, right? There's a very geometric picture that you can have in mind. These are the corners of the cube that you're interested in. And then you start from 0, and then you can follow one branch of that tree. And somehow you approach a corner by traversing it by going from parent to child, etc. Additionally, the law of these MTs, so you can look at this MT and it's a martingale. So this MT, just by the fact that if I condition on a cluster and I look inside it and I look at a cluster inside it and I look at the barycenter of that, then what do I want to say? All right, forget this. No, I think I did it the wrong way. MT is a martingale as a function of t because you're doing averaging. You're averaging and then averaging subclusters. So the averages of the averages is the original average. That's what I wanted to say. So these are martingales. And we understand their law. And their law is given by the solution of this PDE somehow. Right, so the law of these MTs is very well understood. And this follows from the analysis of the variational principle from the Parisi formula. So the idea that we had is to choose these nonlinearities in this algorithm so that the ZT that we get out of it mimics the law of this martingale MT, okay, for large K. So what do we know about MT? We know that at 0, it starts at 0. It's a martingale, it diffuses. And at time t equals 1, you know, at the end, it converges almost surely to a corner of the cube. So that's step 1. And then you can try to compute the correlation, the edge correlation between two vertices that are neighbors of each other. And it turns out that just by the properties of the law of this MT, since it's defined by the Parisi formula, you'll get the P star that you're looking at, that you're looking for. And this plus minus 1 depending on which problem you're looking at. So there's a lot of stuff hidden here. There's a lot of stochastic analysis to get this to work out, and there's a lot of approximations to discretize the continuous time dynamics, etc. Okay. So I think I'm going very fast. Time is it? No, I'm not going very fast. I am not at all. But we are at the end. Okay, so there are many open problems here. I just selected 3, but I can say other ones just out loud. Of course, there's the question of establishing perhaps explicit limits of these quantities C plus and C minus as a function of K. Turns out that recently, perhaps in the last 2 years, we have formulas, one that is conjectured in physics, and another one that was proved by Will and Amin and some of their collaborators at the positive temperature, in the positive temperature case. So presumably, if you take that formula and you take beta to plus infinity, you should get something that represents the maximum cut value. But those formulas are extremely complicated. Like, it's not clear that they offer any level of complexity reduction to understand what's going on in max cuts. They're just as complicated as the original formula that's defined with a limit. Right? So there is no idea, there is no insight into what the problem does by looking at those formulas. It doesn't tell you anything. Okay, so that's a hard problem. Questions perhaps that are slightly more practical. So the first one is this. So if you look, okay, I don't know how to compute the exact values of these quantities, but I can look at upper and lower bounds of those quantities by using the first and second moments method. So there's a lot of work on this, and David has a very nice paper on the first and the second moments, upper bounds and lower bounds on these quantities. Let me draw them as a function of K. So for every K you can try, you hope for a bound, upper and lower bound. So I looked at all the bounds that we know from the literature as a function of K. So the upper bounds do this. And the lower bounds that we know also do this. No, so okay, let me rescale this in a better way. I don't know, something like this. So these are the upper and lower bounds of this quantity that I rescaled. So here I subtracted the trivial term, I divided by what's perhaps you can call the standard deviation if you'd like. And then you get something non-trivial now happening. And you can try to draw this as a function of K. Of course, since we don't know the exact value, I just looked at the upper and lower bounds. And they're decreasing, so perhaps it does look like this. So that's one question. So can you show that this is a decreasing function? Of course, the theorem of Dembel-Montgomery and Sand tells you that if you let K go to infinity, this quantity is going to go to P star, right? So P star is here. Okay, so prove this picture. Is this true, right? So in which case, so this is an asymptote. So what does this mean? It means that P star is, so the worst case scenario happens when K is large, which means that for K equals 3, the value of maximum cut for K equals 3 is way larger than P star. So one question, can you get this P star for K equals 3? Right, K equals 4. For K equals 3, can you give me an algorithm or just show that the maximum cut value is larger than P star when you rescale it like that, right? So that's one question perhaps that could be approachable. I don't know if some kind of sub-additivity argument could work here, something like that. I don't know. Right, so algorithms, of course, and then once you show that it's larger, can you actually give an algorithm that achieves that bound? And the main question here is perhaps to construct, this is the underlying hard question in this problem. is to construct a maximally correlated binary valued factor of IID for any fixed k. Any fixed k, can you construct a factor of IID? It has to be binary valued, and that is maximally correlated across an edge, or minimally if you'd like min bisection, whatever, which one you prefer. Okay, I'm done. Thank you. Yeah, of course. Yeah. No, so you have to. So what's going on? So for SK, you have a matrix. You have a GOE matrix, and that's all the randomness that you can rely on. And you use this approximate message passing technology to prove that you can reduce to this PDE. You convert the scaling limits of this algorithm is the PDE, right? But here you don't have a random matrix. You're going to have to simulate that randomness from the randomness around you and far from you, right? So the only randoms that you have are the labels of the vertices, right? No, here the graph is fixed as far, and I'm saying that doesn't help. Like even if you have a random graph, I don't know how to exploit that. The only thing that I'm exploiting is the labels, the randomness of the labels. So I'm gonna have to like go around and gather them and do some central limit theorems and whatnot to somehow simulate the right types of objects that I need to construct the PDE. Here's what I had in mind. Yeah. Say. Model initiates in spot random graph have the same value for the optimization problem because it's originally done by them differently, but then typography using the universe method. Maybe you can use the universe method to apply directly to the algorithm performance and just say that whatever the algorithm gives you in the initial case, it will be corresponding to the spot random spot graph. So the algorithm is not the same one. So that's the first thing. So you're going to have to interpolate between algorithms. I don't know. The algorithm is just not the same. It's not the same algorithm. Somehow they simulate the same dynamics in the limits, but it's not the same. They don't have the same structure. We can talk more, but it's not clear how to couple them. There's no obvious coupling of the two approaches. Let me see. Yes, I can. So it's a crime to erase this. Right, so the PDE that we have here is, you can rephrase it in a dual form as a stochastic control problem. And the idea for the algorithm is just discretize the stochastic control problem so that, doing the approximation from discrete to continuous is something that you can try to do, but let's just try and analyze the stochastic control problem. So the control problem is you want to look at the behavior of this martingale MT that is supposed to represent the barycenter of the cluster at level T of this tree. And the no overlap gap property says that this is somehow continuous in time, so it doesn't jump. It doesn't jump very far. You cannot have a martingale that from a certain T plus from certain T minus to a T plus, it does something crazy. So that's more or less how it works. So it turns out that if you're only interested in the mean field case, no sparse graphs or anything, even in the case where there's overlap gap, you can construct a slightly modified optimization problem where you're not optimizing you're optimizing the same objective function, the P of gamma. This is the Parisi formula, but I'm not optimizing it over non-decreasing functions. I'm optimizing it over all measurable or all continuous functions, let's say. And it turns out in situations where there is overlap gap, the optimal solution looks like this. It doesn't look like this. It looks like it's like genuinely not increasing. It looks like this. And this is a fine solution to work with the algorithm. You can plug it in the algorithm. It'll give you something. It'll give you a value that is strictly smaller than P star for models for which there is no overlap, like P-spin, the P-spin model. So you get a value, right? The algorithm still works. It gives you some value. It's not the optimal one. So the question is whether you can bridge this gap. Can you have an algorithm that bridges the gap? The answer is no. So this was mentioned by David. There is a very, very sophisticated notion of the overlap gap property that you can apply to this problem. And it says that no algorithm can beat the value that is given by this approach, the stochastic control approach. So you have to construct a really intricate tree of restricted overlap patterns, and you can show that in the limit is magical, that gives you this optimization problem over non-monotone functions. It's some beautiful work, yeah. Other questions?